Today we will discuss single phase full wave uncontrolled rectifier for R and RL load and its harmonic analysis. So this is a single phase full wave uncontrolled rectifier with resistive load. So load resistance is connected. This is your supply voltage and this is a full wave rectifier. So when this is a positive half cycle is applied here, D1, D4 are forward bias, and in the negative half cycle D3 and D2 are forward bias. So if you see, this is 2 are forward bias, and if you see, this is our current path when the positive half cycle. Okay, in the positive half cycle you can see this is your path for the current, and you can see that the current IS or the supply current is positive, and during this V0 is equal to Vs in the positive half. And in the negative half cycle, if you go this negative half cycle D2 and D3 conduct, you can see the what is the path for the current is D2 R and D3, and then through this Vs positive and negative. So you can see that the Is is negative here. So you can see here, this is our output voltage waveform, and voltage across the D1, D4, you can see that there are full voltage across that, and then you can see this is your V0 by R as the same waveform as this Vs, because it is a resistive load. Then we will find out what is the output voltage. Average output voltage is, you can see that from here 1 by pi 0 to pi Vm sin omega t d omega t, which is 2 Vm by pi, and the average value of the load current is nothing but I0 is V0 by R, which is 2 Vm by pi R, and output power is V0 into I0, this is the V0 square or Vdc square by R, and VO RMS we got the Vm by root 2. And you can find out the load current IRMS, IORMS is nothing but VORMS divided by R, which is Vm by root 2R, and output AC power is VORMS and IORMS, which is nothing but VORMS squared by R, and this is the 0.707 Vm whole square by R. And the average value and RMS of the supply current IS, if you average you find out, because it is sinus, you can see that both input and the sinusoidal, so you know that this average is equal to 0, and RMS also will come around Vm by root 2R. Now this is our single phase full wave uncontrolled rectifier loaded with a highly inductive load. That means it is the like a constant current source, and this in the positive half cycle, you see this is a supply voltage. In the positive half cycle, D1, D2 are turned on. As soon as D1, D2 are turned on, this is the path. You can see this is the path for the current flow from this Vs positive, it will go to D1, then the load, and through this load then it come to D2, and again it go back to this. This is the loop current. Okay, so this is current. You can see that the this is the diode will D1 D2 conduct, and you will get the positive half cycle of the rectifier. And then this is your Is is a positive. I have shown here marked this this is marked, and this is your Is, which is positive. Okay, because the load current is the constant. Then the negative half cycle, the D3 and D4 will conduct. So you can see that it will the Vs negative will come through D3, then the load, and from their load to D4 to again it go back to the source. So this is what the negative half cycle another peak comes, and you can see that in the negative half cycle you can see that the voltage, although the voltage is unidirectional or output voltage is not, whereas the input supply current you can see here it is this negative current or minus current during this period. Now if we will find out what is the average voltage, output voltage, V0 is nothing but, you can find out by using this formula, which is nothing but 2Vm by pi, and I0 is nothing but V0 divided by R, which is 2Vm by pi R, and the DC power is V0 I0 or VDC squared by R. And if you find here what is the VORMS, you can find from here VORMS is Vm by root 2 and VORMS is divided by R, or VRMS divided by R. And since the load current is constant over the studied period, therefore the RMS value of the load current IORMS is nothing but IDC, which is equal to IS average. The output AC power is given as VORMS into IORMS, we get this. So the harmonic of output voltage, you can see that it is a pulse setting. Okay, we have got 2 pulse converter. Okay, this is full wave means 2 pulse, single phase full wave converter, 2 pulse. So in 1 pulse we try to express this in a Fourier series, and you can see that this is 1 pulse, and which I have taken the cosine equivalent, because this cosine equivalent will be very easier for us to, you can take also, there is no problem. So the Fourier series we can represent by this equation. Okay, so then the coefficient A0, AN and Bn need to be find out, which is defined here in these 3 equations, A0, An and Bn. Once you find out, you can see that A0 is VDC, which is nothing but, if you take the integration, this coefficient will come to Vm by pi, and the Fourier An, which is nothing but 1 by pi minus pi by 2 to pi by 2, and Vm cos omega t cos n omega t d omega t. So if you find this one, what is this is 4 Vm by pi, and this is the equation. And Bn, you know that this Bn is equal to Vm cos omega t sin n omega t d omega t, it will be 0. So if you find here the Cn, or the nth order harmonic, Cn can be found out an square plus Bn square root over, and the phase angle of the nth order harmonic is phi n is tan inverse An by Bn. The output voltage waveform expressed in the Fourier. So this, if you put all this in the Fourier series, you will find this is the Fourier series of this waveform. So here you can see that this, if you see, this is our Fourier series. The first term of the RHS is the DC value. Okay, this is a DC value, or sometimes we call offset, DC offset. And the second term in the dormant output ripple, which this case at twice the supply frequency, you can see 2 omega t. Okay, the second term. Okay, and the third term, the third term are the higher order, 4 omega t, then 6 omega t, like that it will go on. Okay, sixth. The amplitude of this ripple reduced as the harmonic number increases. You can see the number of harmonic increases, the second order, third order, fourth order, you will find that 15, 1 by 35, that it goes increasing. So the this will be the the ripple reduces. All components, all these components are unwanted, because if they are higher order harmonic component, this you can define like this. And if you see here, you can see that the first is your DC offset, and then you get the second order, then fourth order. Okay, the second order is 2 into 50 hertz, which is 100 hertz. You can see this frequency, and fourth is your 200 hertz, and like that, as it grows, the amplitude reduces. So similarly, I have just given this Fourier series of our half wave rectifier, and you can derive this one and try to understand that this is your half wave rectifier. So if we see the single phase half wave rectification, the source current we have seen, it is like a square. Okay, the positive, it is alternating, but it is a square like a thing. So if you see this one, you can understand that this IFSW is which is IDC for 0 to pi, and minus IDC is 0 to pi to 2 pi. Okay, so you can find out the coefficient for this one, and if you find out the A naught will be equal to 0, and you can see that the A naught is 0 because you can see from the plot of this one, because there is no DC component. Okay, alternating component, and A0 is 0, AN is also 0, and Bn you got the IDC by n pi into 1 minus cos n pi. So when you just expand this one, we know that this Bn is equal to 0 for 2, 4, 6, all thing, and only the odd values like 3, 5, 7, you will find that this is minus 1. So if you find out this, if you expand this one, this is our expansion of our the Fourier series. Okay, you can see that there is a fundamental component which is only omega t, sin omega t. Then third order harmonic component, or third harmonic component, which is called the 3 omega t. It is called third harmonic. Third harmonic means it will oscillate 3. You can see that 1 into 50 means around 150 hertz. And then fifth harmonic component is 5 omega t. Like that, you go on adding all this. So if you see here, this is the first one is your first order harmonic, and third one is your third harmonic, fifth, seventh, ninth, and these are called the harmonic spectrum. So these are called the harmonic spectrum, by which you can understand and the what is ripple content in your output voltage waveform or the input current waveform. So once you know that this is my harmonic, you will try to design a filter which you can filter out the harmonic from the input and output voltages from the input currents. So this is the beauty of the harmonic. Is nothing but like a river flows, there are a lot of drainage are connected to the river water makes pollution. Similarly, in our transmission system, transmission line are there, and pure power actually it is flow, but due to connection of different nonlinear devices, and especially the power electronics converter devices like laptop, Xerox machine, everything, they draw non-sinusoidal current, and which affect on the transmission system. They also draw non-sinusoidal current. Because of that, they pollute, like we pollute the river. Exactly, it is polluted in our polluted in the power system. So this is what the harmonic. And thank you.